Hello student, in this video we will study about the valence bond theory and hybridization. So basically this is the extension video about the hybridization. In the previous video we have already studied about the valence bond theory and hybridization. So let's focus one more time what is the meaning of hybridization and how it is work here. So hybridization are like sp and sp2, sp3, sp3d and sp3d2, and these are mainly for central atom, and how they are correlated with the electron pair geometry. So if a molecule have linear electron pair geometry, only two things around the central atom, then the central atom will have sp hybridization, and it have two equivalent orbital. What does it means? I will explain you in next slide. So in the trigonal planar electron pair geometry means there are three things around the central atom, and the central atom will have sp2 hybridization. In case of tetrahedral, four things are around the central atom and the hybridization will be sp3 type. Trigonal bipyramidal, five things are around the central atom and the sp3d hybrid central atom will be sp3d hybrid. And in case of octahedral, when the six thing are around the central atom, the central atom will have sp3d2 type of hybridization. So what is the meaning of this hybridization? Let me explain this hybridization with one example. So in case this is very simple example to understand the hybridization. Suppose you have 3 cups of coconut milk or coconut cream and 5 cups of pineapple juice. So and you want to give it to your friends, but you want to make them equivalent. So what you can do, you can mix all these two together, all these 8 cups, 3 cups of coconut and 5 cups of pineapple, and redistribute the 8 cups again. So what will you will get? You will get 8 cups of pina colada. So and this pina colada is will have equivalent taste and energy compared to only coconut cream or coconut milk and pineapple juice. So this process is mixing and redistribution is called hybridization, and the end product, which is the pina colada, is called a hybrid. So this is a hybrid or cocktail type of mixture. So this is the same process happen for the central atom in case of hybridization. So here this chart is, once again I will explain that all the hybridization is based on the electron pair geometry. So if electron pair geometry is linear, hybridization will be sp. If so basically these sp means there are two sp orbitals, 1 and 2. So these will be two sp orbital. An example is Bf, beryllium difluoride, mercury chloride. Trigonal planar, then sp2 hybridization. Tetrahedral, there are 4 things, so 4 sp3 hybrid orbitals will be there. In case of trigonal bipyramidal, sp3d. In case of octahedral, there will be sp3d2 type of orbital. And these are the some examples. So let's see next slide where we can see some examples. So this slide shows that water have, when we will draw the Lewis structure, it have 4 things around the central atom, and in case of 4 thing or tetrahedron will be geometry, electron pair geometry, and then we need the central atom would be sp3 hybrid. In case of carbon dioxide gas, the 2 things are around the central atom, the hybridization will be sp type. In case of CH4, 4 things are around the central atom, sp3 hybridization. In case of SO3, three things around the central atom, and sp2 hybridization will be there. Likewise SF4, when we will draw the Lewis structure of this one, we will get five things around the central atom, and the hybridization will be sp3d. So let's review these examples one by one. So as I have shown you that let's talk about the carbon dioxide gas. So carbon dioxide gas, when we will draw the Lewis structure of this one, you will notice that there are two double bonds around the carbon, and carbon electron pair geometry will be linear. So two things around the central atom. Basically, in case of double bond, there will be 1 sigma and 1 pi. So 1 sigma, 1 pi, 1 sigma, 1 pi, and the electron pair geometry will be linear, and the hybridization will be sp hybrid. So when you will write the electron configuration of this one, it will be like 1s2, 2s2 and 2p2. So you will notice that these are the valence electron, and we are talking only here about the valence electron and valence orbitals. So these two orbitals or valence electron are in a different energy, exactly like one is coconut water or milk and one is pineapple juice. So what we have to do, basically this is a kind of mathematical operation which atoms do based on the quantum theory. They mix together these orbitals and redistribute the energy to make two equivalent orbitals for the bonding with the carbon dioxide gas. Basically, the pi bonds are formed by the p orbital overlap. So there are two p orbitals are empty, and but the sigma bonds are formed by sp hybrid orbitals. So you can see these two orbitals have only one electron, which are coming from the hybridization, and in case of sp hybridization, only one s orbital and one p orbital is taking place. That is why it's called sp hybrid orbitals, and each orbital have one electron. Then it can share another electron with oxygen to make a double electron pair. So similarly, this is the example for the sulfur dioxide, where we have seen in this case sulfur trioxide. Basically, this is sulfur trioxide. So in case of sulfur trioxide, three things are there around the central atom. So three things are around the atom, and when you will draw the Lewis structure of this one, you will notice that this is a trigonal planar, and all sulfur have 3 sigma bond and 3 pi bond. So for making hybrid orbital, what sulfur does, basically sulfur uses its valence electron. So once we will write the S3, so 1s2, 2s2, 2p6 and 3s2 and 3p4. So these are the 6 valence electron, and it need to make a 3 sigma bond with the oxygen. So what it does, it makes mix 2 of the p orbital and 1 of s orbital, and redistribute the electron in such a way so that they get 3 sp2 hybrid orbitals and 3 p orbital contain only p electrons. So they use this for to making pi bond. In case of CH4, so electron pair geometry is tetrahedron. 4 things are around the central atom, and you can see all the 4 bonds are single bonds, so they are sigma bond. And once you will write the electron configuration, so it is 2s2 and 2p2. So carbon need 8 electron total, and in case of if it is already s2 and they have two different types of energy, so what it does, it uses all three orbital from the p and one orbital from the s, mix it and redistribute to make 4 equivalent orbitals which contain one electron only, so that they can have another electron from the hydrogen to make it 8. So these are the way about the hybridization occur. Let's see another examples in case of water molecule. This is again tetrahedral, and you will notice that this time it has only 2 single bond and 2 electron pairs are remain. So oxygen is the central atom, and we will write the electron configuration 1s2 2s2 2p4. so you can see there are 1 2 3 4 5 6 valence electron are there, but they are in different energy levels, so they need to be mixed and redistribute so that they can get they can make their equivalent orbital for the bonding. So they make 1s and 3p orbital to make 4sp 3 hybrid orbitals, where two orbital have only single electron, so that they can share with the they can accommodate one more electron from the hydrogen, and remaining the electron pair is sp3. So this is sp3 type of central atom. And in case of SF4, there are this is a trigonal bipyramidal, and the electron pair geometry is trigonal bipyramidal, which is 5 things around the central atom. And how they make the hybrid orbitals, they uses the empty d orbital also, because you can see 2s2 2p4 and then 3d 0, means d orbital is there but it is empty. So sulfur can utilize its empty orbital also to make hybrid orbitals to it. So it make 1 2 3 4 5 hybrid orbital, which is called sp3d, because it uses 1s and 3p and 1d orbital. That is why it's sp3 hybrid central atom. So you can see it make a 4 single electron containing orbital, and then it can accommodate 1 electron from the fluorine to make its octet complete, and 1 lone pair is remain as such. So all the hybridization are based on the electron pair geometry, not based on the molecular shape. So this is important. And last example is here is octahedral, means 6 electron domain or 6 thing around the central atom. And when you will write the, for an example is Cl pentafluoride, chlorine pentafluoride. So when you write the electron configuration, you will notice that chlorine has valence electron in the third shell, 2s2 2p 3s2 3p5 and 3d 0. So its d orbital is also empty, but to make a 5 bond with the fluorine, it mix all these orbital and redistribute to make a 1 2 3 4 5 6, basically 1 2 3 4 5 6 sp3 d2 equivalent orbital it makes, and where 5 will be unpaired electrons. 5 orbital will contain unpaired electron, so that they can have pairing from the fluorine atom, and then 1 lone pair will still remain, which is here this one. So this is the way you can understand what is the hybridization and why they are forming, and all these hybridization are based on only electron pair geometry. So let's summarize once again that as we have seen in the previous slide, this one, or in this one, that and you can add the hybridization values also in this chart, that if the geometry is linear, if the electron pair geometry is linear, then the central atom will have sp hybrid, and in case of trigonal planar, this one, the hybridization will be sp2 type. In case of tetrahedron, hybridization will be sp3 type. In case of trigonal bipyramidal, sp3d, and last one is octahedral. In case of octahedral electron pair geometry, the central atom will have sp3d2 hybrid orbitals. So hybridization is basically the process to make equivalent orbitals for the bonding, so that they can make equivalent bonds with the all 4 bond or 2 bond or 5 bond will remain in the same strength or same energy level, otherwise they will be different energy level. Okay, so this was all about the hybridization and their electron pair geometry correlation and how hybridization works. So I hope you will understand this one.